So we made a slight shift in the program and had lunch before Yair and gave Yair Weiss the difficult task of speaking right after lunch. I'm sure if anyone can do it, he can. And so actually I had some complaints from people here that didn't quite understand the connection between security and this workshop. Let me just say again that this workshop is supported, as you can see, generously by NATO under the program of Science for Peace, or Science for Peace and Security. And we emphasize that what we want to do here is to study the connection between machine learning and video to present, particularly for the topic of our research. But I allowed myself to extend it and make it a little more interdisciplinary and give some topics that I hope you enjoy, even if you don't hear about it every day. And those who want to do other things like information security is very much on my mind as well. I'm most welcome to organize another workshop like this next year or whenever. So I really think that having a very narrow community only is a little boring. I hope that you enjoy this interdisciplinarity, this is the spirit of this session. Yair, please.
Thank you. Actually, Tali gave a great introduction because I think this talk has nothing to do with security.
No, we will find a connection.
But if anybody can find the connection, Tali can. I think one thing that obviously happens if you work with video surveillance data is there's just lots and lots of data there. That's, I think, a strong connection. And this fact that we now have lots and lots of visual data is the motivation for this work, which I should say in the beginning is a joint work with Rob Fergus, who's at NYU, and Antonio Torralba at MIT. And what the motivation for the work from our perspective was really this fact that we're in a very different time now of doing computer vision. When I was doing my PhD, the number of images in all computer vision papers was about 5. And we actually knew them by name. There was the Lena image, the Barbara image. You actually could give a name. What? Yeah. Well, I'm not touching on video. There was one video. It was called the Flower Garden Sequence. It was one video. And now, of course, we live in a world of every one of you has on his cell phone thousands of images on his PC, tens of thousands of images on his Picasa website, maybe more. If you look at something like Google, we have a much, much larger number of images. And I think this is a fascinating time in that sense to be doing computer vision research. This image over here is an illustration of a database that was collected by my 2 co-authors before I joined this project. It's called the Tiny Image website. You can Google for it by writing Tiny Images. And what it is it's a collection of 80 million images. And it was collected in the following way. You take every noun in the English language, every noun, there's about 70,000 nouns in the English language. You Google query image search with that noun. Every noun will return about slightly more than 1,000 images. And you do 70,000 times a little bit more than 1,000, you get 80 million images. And what this displays is that there are 70,000 squares in this image. Every square is the average of the first 10 images returned to that query. So this is sort of a visual map of the English language. And it's organized semantically. So over here are all the words related to plants. Over here are marine animals. And in a sense, every word in the English language appears somewhere in this map. This was, I don't know how many people here have heard of Slashdot, also known as the news site for nerds. So this appeared on Slashdot, and it's a funny thing about human nature that about 1 hour after it was posted on Slashdot, someone posted the coordinates of where the pornography was. But I'm not going to tell you. If you want to search during my talk, you'll have to do it on your own. Yeah, the other thing I want to say just about this database, that it took about half a year to collect 80 million images at MIT and to store them on the servers. nowadays, this was done about 5 years ago, nowadays this is considered a small data set. So I don't know, number of images indexed by Google, does anyone have an idea? It's on the order of 3 billion. So this is 80 million, that's 3 billion. And the number of course, the largest repository of images on the web is Facebook, where it's about 100 million images per week are uploaded to Facebook. So yes, 100 million per week. This is true for last year, probably it's grown more. Maybe to put this into perspective, so if you think of the handful of images that I was working on when I was doing my PhD, that's like a small family. If you think of data sets like that we worked on, like the Corel data set, which is 30,000 images, it's like the population maybe of Nevaseret. 80 million is the population about of West Germany. 3 billion is, half the population of the world. And 100 million per week, it's as if 1 in every 5 Facebook users uploads 1 image per week. But of course, these are gigantic image collections. That's the title of this. Okay, so I think my talk is really, I wrote a research grant, and I'm very keen on the general question of what can we do with so many images. Surely it's going to buy us something. The fact that when I was doing my PhD we had 5 images, and now we have billions of images, surely it's got to be good for something. And I'll talk about one particular very narrow project. So that's sort of the broad idea is what can we use these gigantic image collections for, but I'll talk about a very narrow topic, which is how to do semi-supervised learning in these very large image sets. The reason that this is, I think, relevant to internet data is if you look at these billions of images that are out there, they come with a spectrum of labels in the machine learning sense, of the desired output. So there's a very small fraction of images on the internet that are human, that have human annotations associated with them, where a human went in and said, this is a motorbike, this is an airplane, on the orders of tens of thousands. Again, think of the population of Nevaseret relative to the number of people in the world. That's about the fraction of images on the internet that are labeled with high-quality labels. And it's interesting that even though I don't know how many people have heard of Amazon Mechanical Turk, it's a way for anyone who wants to post tasks on the internet and allow anyone on the internet who wants to try to solve that task for a very small amount of money. And it's very good for academics because the whole financial transaction is very, very simple to do. Every one of you can set up an Amazon Mechanical Turk task tomorrow, and you don't have to, you give your credit card number, and Amazon is actually the one who does the payment. So it's very, very easy to set up, and people all over the world can participate. And even so, though there are so many bored people out there on the internet, still the number of labeled images is in the tens of thousands only. It's hard to get people to do this long-term and large scale. So that's a very small fraction. There's a much larger fraction of images that have noisy labels, and these are basically the surrounding text around that image. So what you're seeing here, this is a slide from 3 or 4 years ago. These are images that were returned 3 years ago in Google image search when you queried for airplane. So I don't know if you can see, probably you cannot, but in this image over here, there's a boy holding a small toy airplane. Here there really is an airplane. This is an airplane engine. This is a drawing of an airplane. And up to about 3 years ago, actually, Google didn't even look at the pixels when it was doing image search. It was just, if the file name was called airplane.jpg, and there was all sorts of other things in the text around the file name, it would be returned in response to the query. So it was very noisy labeling from a computer vision standpoint. So you have that for many images, but of course there are also images that don't have any text around them, like the images on your digital camera, the images you upload to Facebook, the images you upload to Flickr, and this is the vast majority of images on the internet are images with just no labels at all. So you have this spectrum of images with very high quality annotations, no annotations, and things in between. And we'd like to be able to do machine learning with all of this spectrum. In machine learning, this type of problem is called semi-supervised learning. Semi-supervised learning is something in between the unsupervised learning case, when we do things like clustering or find outliers, as was mentioned in the previous talks, or estimate the covariance. That's an example of unsupervised learning. Fully supervised learning is like when we talked about face detection. So you're given a lot of examples of faces, a lot of examples of non-faces, and you train the classifier to separate between those. And semi-supervised learning is everything in between. Specifically, the general setting is we have many, many unlabeled data points and just a small fraction of labeled points. In this case, there are two. One labeled red, one labeled green. If we ignore the unlabeled points in a fully supervised algorithm and just find something like an SVM, we find this hyperplane. And if we then translate that into the unlabeled points, we would get a separation of the points that look like this. And somehow this doesn't seem right. And just intuitively, it splits these clusters into half. There seems to be a much more reasonable way to split the data if you take into account both the unlabeled data and the labeled data. And that's really the role of semi-supervised learning. Somehow using both the unlabeled data and the labeled data. And the general idea behind semi-supervised learning is you want your classification function to be smooth with respect to the data density. So you allow it to change from red to green, but you don't want it to change from red to green in a place where there's a lot of points. So here we change from red to green in a very high density region. That's bad. Whereas here, the change from red to green happens in a place where there's no points, and we think that's much more reasonable. And the way this is typically formalized, this goes back to Tali's talk this morning, is using the graph Laplacian. So we take our points and we build a graph where every vertex of the graph is one of our data points, and edges are exponential in distance. So here we have a strong weight between these 2 points, because they're close, and a much weaker edge between these 2 points because they're far away. And more generally, we can think of this graph as a matrix, where the ijth element is e to the minus the Euclidean distance between them, point I and point j. And using this, we can define something that Tali already mentioned, the graph Laplacian, which is a natural way to measure smoothness with respect to data density. That's one way to think of the graph Laplacian. It generalizes the notion of smoothness that also Ami mentioned in his talk, and regularization, but it's a data-dependent smoothness. It's a notion of smoothness that penalizes much more in areas of space where there's a high density of points. So more mathematically, this is the way it happens. We take our matrix L, and we have a vector F that assigns a function to every data point. And the way we would measure smoothness is using this quadratic form, F transpose times L times F. One can show this is a positive definite. It always returns a positive number. And the larger that number is, the less smooth the function is. So the most smooth function would have F transpose LF equals to 0. That would be a constant function. And in general, the higher this is, the worse. The less likely or the less smooth the function is. And in semi-supervised learning, we also have this other term which says that we want our F to agree with the labels in places where there are labels. And the nice thing about semi-supervised learning in this particular formalism is that we minimize the this is quadratic and this is quadratic, so we can just solve the linear system of equations and obtain our desired classification function, which is again satisfies the labels, but it also takes into account the unlabeled data. So that was semi-supervised learning in 2 slides. The problem with this, one problem with semi-supervised learning that was realized very early on is that the size of the matrix that we need to solve here, the linear system that we need to solve, is the size of the graph, which if we have n points, it's an n by n matrix that we need to invert or solve a linear system. And if you're a computer scientist, you don't care because you say, oh, it's polynomial time, we don't really care. Inverting a matrix is n cubed. But when n is very large, these things become very unwieldy. You don't really think of n being the number of images on the internet. You don't really want to invert a matrix that large whenever you do classification. So this was realized by a number of people that it might make more sense to actually reduce the dimensionality of F by restricting ourselves to linear combinations of eigenvectors of the Laplacian with small eigenvalues. So just to illustrate this idea, again, I think Tali talked about the eigenvectors of the graph Laplacian. Here's a data set. We calculate the graph Laplacian, take its eigenvalues, and if you remember, what is the definition of the eigenvectors? Is it's the smoothest, it's the first eigenvector is the vector that minimizes F transpose LF, right? And I told you it was a positive definite matrix, so that the smallest that number can be a 0. And what's the smoothest function? Again, it's a constant function. It doesn't change at all, so it has the smoothest. F transpose LF equals to 0. The second eigenvector has to be orthogonal to the first one and also be smooth. And you see it gives us a very nice separation of the data into two classes. And then the third eigenvector, again, has to be orthogonal to the first two and also be very smooth with respect to data density. This is what it finds. And you can see that our desired classification function is a linear combination of these three vectors. In fact, it only needs the second vector. It's a linear combination of only one. So that's the general idea behind this word going back to Belkin and Iogi. Instead of trying to solve a linear system, which is the size of your original data set, restrict yourself to, say, k, say 100 or 50 eigenvectors, and find the best linear combination of these eigenvectors that satisfy the supervised constraints. And so again, you need to solve only a linear system of equations, but now it's a k by k system, where k is usually 100 or 50, some user parameter. And of course, we can solve this much more quickly than inverting the full million by a million matrix. Okay, but the reason I'm giving this talk is that there's still research to be done here, is that either way you look at it, you still have a computational problem. We can either directly solve the linear system defined by the Laplacian, but if you have a data set of 80 million images, you have to invert a matrix which is 80 million by 80 million. The other approach, I told you only have to solve a system of equations which is 100 by 100, but I left out the part that you need to find these eigenvectors. So you need to diagonalize an 80 million by 80 million matrix. That's also very expensive. So really the subject of this talk is how can we still do semi-supervised learning without doing any of these two operations, which although polynomial time are not things we want to do. Every time someone searches for a term in Google, we don't want to resolve each of these two tasks. We're not the first people, this has nothing to do with images in a sense. Every time you have a large data set, this is an issue. And people realized early on when they were doing semi-supervised learning that there must be a way to avoid this curse of not of dimensionality, but actually the curse of lots of points. It's a very embarrassing fact about machine learning is that our theorems are always about, when we have lots and lots of data, everything works better, but our algorithms actually work a lot worse because they start slowing down. Well, maybe Shai will talk about it. Shai here? Shai might, are you going to talk about it? No. But Shai's work being one of the few exceptions, most work in computer vision, actually, when you do machine learning, finds it very difficult to deal with very large data sets, even though that's really the interesting regime, that's where all the data is. But one way of solving this problem is known as the Nystrom method. It's a classical approach in applied mathematics, and basically, applied to this setting, it says, instead of taking the full data, subsample the data to get a small set of landmarks that are representative of the full data set. You calculate the eigenvectors on this set of landmark points, and you interpolate them to the rest of the data points, and that's really what the Nystrom method allows you to do, how to go from the eigenvectors, say, of this 50 by 50 matrix, what would the eigenvectors, to approximate the eigenvectors of this, say, million by million matrix. That's what the Nystrom method does, and it's linear. It's a linear time algorithm, and therefore it's applicable. I was not around at MIT when they collected this data set, but my co-authors were very unhappy with this solution because it took them half a year to collect 80 million images, and then Nystrom tells me, throw all them away, just choose a random subset of them and do all the calculations on these. It's very unsatisfactory. You really want to be able to use all the data. There are other approaches that don't randomly throw away the data, but somehow cluster the data and then do the semi-supervised learning on the clusters. The issue, of course, is that clustering 80 million images could also be very expensive. Those algorithms can often be expensive as well. And so they're actually these approaches are seldom used in practice. There's a dominant approach. It's Nystrom. You just subsample, you take a random sample of the data, and work with that. Okay, so our approach is similar to Nystrom, but the opposite. So whereas Nystrom takes this data set and subsamples it to reduce the N, we're going to go in the opposite direction. we're going to increase n, and we're actually going to take the limit as the number of points goes to infinity. Sort of surprising, I think the nice insight behind this paper, sometimes it's easier to work with the infinite limit than with a finite amount of data. So we're actually going to consider the density, when you assume that these bit points were sampled from a density. If we sample an infinite number of points from that density, it will approach, obviously, the PDF of the density, and we're going to work with the PDF and not work with the original data points. This gives us an algorithm that's linear in the number of data points, whereas Nystrom is polynomial in the number of landmarks. If the number of landmarks is small, then Nystrom is very efficient, but again, throws away a lot of the data. Okay, so just to give some intuition about this, consider X again to be drawn from a two-dimensional distribution, P of X. So we have all these data points over here, but they were actually samples from some underlying continuous density. And we're going to forget about the samples and think about the density. That's the main conceptual idea here. Think about the density, forget about, and then the number of points doesn't matter anymore. It's infinite. The density is really the focus of our attention. And just as one could define this graph Laplacian, which is a discrete operator, you can also define a continuous smoothness operator that, given any function in two dimensions, returns a number that says how smooth that function is with respect to the density. And it basically penalizes for derivatives of the function in areas where there's high density, and doesn't penalize for derivatives of the function in areas where there's low density. But the important thing is it doesn't care about the number of points anymore. It's a continuous function. It gets a continuous function as input and a continuous density, and it penalizes for the smoothness weighted by the density. So the n has disappeared from our equations. And just like the original operator had eigenvectors, this operator has eigenfunctions. And let me draw them. So this was what I was showing earlier. These were the eigenvectors of this discrete set of points. And this is the density. And this density defines a smoothness operator, a positive definite operator. And it has eigenfunctions. And these eigenfunctions also have a smoothness value. So this is the smoothest function available. Again, it's the constant function, it doesn't change at all. So it has an eigenvalue of 0. The second smoothest function has to be orthogonal to this one, so it splits the rectangle into two parts. And then the third eigenfunction looks like this. And you may or may not notice that there's some similarity between the eigenvectors on top and the eigenfunction in the bottom. And there's a mathematical theorem that tells you that when the number of points goes to infinity, the eigenvectors approach these eigenfunctions, and the eigenvalues approach the eigenvalues that I'm showing in the bottom. So you see that you have 0, 0.002, 0.035, you have 0, 0.002, 0.038. That's not a coincidence. As the number of points will increase, both the eigenvectors and the eigenfunctions will agree. Okay, so that's great. Now I forgot about n, because the number of points doesn't enter into the equations anymore, but there's still the question of the number of dimensions.
How do you generate continuous density?
I haven't told you, haven't missed it.
Okay.
In general, I just need to estimate the density. Instead of having the curse of the number of points, I have the curse of dimensionality. Because to estimate a continuous density in 30 dimensions even is very hard. So the key assumption that we're going to make now is an assumption of separability of this distribution. And we're basically assuming separability assumes that the joint distribution is a product of marginal distributions. In other words, that the density is such that the two dimensions are independent. And of course, this is a very strong assumption, and we'll talk later about whether it makes sense or not to make the assumption. But the nice thing is that if there's a theorem that says that if the separability holds, then you don't ever have to calculate the eigenfunction of the joint density. In fact, you don't need to know what the joint density is. Everything you can do with just densities along single dimensions. So the curse of dimensionality doesn't appear anymore because you don't need to estimate ever the joint density. It's enough to estimate marginal densities, and from that you can calculate everything you could from the joint density. So that now gives us an algorithm. If we assume, like in this case, we assume separability holds, we get the data, we calculate marginal distributions. For each of these marginal distributions, we numerically solve for the eigenfunctions, which ends up being a linear system of equations that we need to solve an eigenvector problem, but it's, again, we don't have n anymore. The complexity of the eigenvector problem depends on the number of bins in our histogram, typically 50. Yes?
If you assume separability, also the PCA problem becomes much easier, right? You just take the largest dimension.
Well, PCA doesn't know about separability, right?
But if you assume, you can use this assumption.
No, even if the data is separable, yes, then and you run PCA on it, you won't just find one of the dimensions pure. I think we're talking maybe about two different ideas of separability, but I'll say maybe your question in a different way. It's true that once the data is separable, you could use the same tricks in the discrete setting. Maybe this is what you want to say. Is that what you want to say? It's true that there are notions of separability, like in digital filtering. Even discrete things can be separable or non-separable. There's also a notion, you can generalize this notion of separability without necessarily going to the infinite limit. But it doesn't necessarily give you much benefit. Is that what you want to say? Okay.
No, this PCA, the vectors PCA and the eigenvectors of the classroom are very different things. And related, of course, both of them are vectors, eigenvectors, symmetric matrix, but the meaning is very different. I mentioned it earlier in the morning. Yeah, okay. Simply a different problem.
But anyway, just to give you a feel for the algorithm, I'll summarize it in a bit, but we take the data, we histogram it along single dimensions, and that's very fast, and it's linear, of course, the number of data points. Once we have that histogram, we solve an eigenvector problem whose complexity is the number of bins. This is also very cheap. And then we can use this. What? What did I say?
Linear.
No, right, it's cubed. It's linear in the number of points. To get the histogram, you have to count all the points, and then you do something that's cubed in the number of bins. Yes. And that gives us the eigenfunctions, which we can then interpolate. We do this for every dimension separately. Now we have a new data point. We figure in what histogram bin it falls. You add the value of its eigenfunction in that one dimension. Oh, sorry. And the basic thing I want to say is that really we can calculate the eigenvectors of this very big matrix very, very efficiently by making these assumptions. Essentially, the sequence of operations I just told you about, but if the number of data points went to infinity and the function, the p of x originally was separable, then the procedure I just described would give you exactly the same answer as taking the eigenvectors of this n by n matrix, but I've totally thrown away the dependence on n. You no longer need to calculate the eigenvectors of maybe union by union matrix. You do all your calculations on histograms. It's linear in n just because you need to build the histograms. But you get exactly the same answer. That's what I'm trying to say. Exactly the same answer in the end if the assumptions were to hold, but much faster. Okay, the important thing, strong assumption here is the separability, and it sounds totally ridiculous to assume that two dimensions are independent. But the thing that is maybe surprising to someone who hasn't studied machine learning is that any distribution can be made uncorrelated by a simple rotation. So that's what PCA does. That's what I was mentioning PCA earlier. So if you don't think about remember that if we have a set of features, we have x, we can rotate it, we can always find the rotation of that distribution so that the different dimensions are uncorrelated. Which is rather surprising when you think about it.
Yeah, but if it's not Gaussian, then of course there may be a high dependency.
Yeah, so there might be higher order dependencies left, but at least the second order dependency.
Also, if it's completely distorted, you need something like kernel PCA to do this.
But at least you can always assume that your data is uncorrelated, which goes back after a rotation.
Sometimes second order is just a small part of the story.
Yes, yes. But and we'll talk about this. But what we do specifically is we just do PCA first. So we get data that at least is uncorrelated, may or may not be independent, and then we hope for the best. The higher order correlations are not killing us. So here's the overall algorithm. We rotate the data first using PCA to make at least the different dimensions uncorrelated. Really we should not be doing PCA, we should be doing ICA, but we're doing PCA. And then for each of the input dimensions, we construct the histogram, solve numerically for the eigenfunctions, take the first K, interpolate them into K eigenfunctions, and this gives us the approximate eigenvectors of the Laplacian, and finally we solve a K by K least square systems to give the label function. And again, the thing I want to emphasize...
You do PCA on what? Not on the whole data set. On 80 million by 80 million metrics.
Yes, but it's...
sample and then you do the PCA?
No, it's funny. There's this Eigenfaces paper, which has, I think, 3,000 citations, and it has only like 2 equations. And what those equations are is showing that if you want to do PCA, on a D by N matrix, you only... Yeah, it's only...
Divide them the square, yeah.
It's only the smaller dimension that matters. It's a very useful trick. I don't know why they ended up publishing in that paper, but anyway, it's here typically the dimension is 32. 32 dimensional vectors. So the thing we do PCA on is 32 by 32.
So you do 900 times the number of data points, then you do it.
Yeah, you loop through all the data you do your linear number of data points to construct that matrix, and then you so it's still linear in N. But it's polynomial in D, but D is smaller. Yeah. The assumption is that D is smaller. The thing I want to emphasize is that this algorithm will give us exactly the same results as the algorithm I was discussing in the 4th slide if the data is separable. So all these steps here where we build histograms and do eigenfunctions and so on and so forth, in the end we get things that are approximation of the eigenvectors of the Laplacian, and if all our assumptions hold, this is an exact algorithm, just to get the eigenvectors of the Laplacian, and then we go back to solving the K by K system of equations. So it's the same algorithm as was proposed by Belkin and Iogi and others, but we just replaced the calculation of the eigenvectors of the Laplacian with a different calculation that's much more efficient and is exact under certain conditions, and in other conditions gives us an approximation error. Okay, so some experiments on Toya data. So here's the data set. Lots of unlabeled points, 2 labeled points. What do you think is the right classification function?
Maybe more than 2.
The camera is not filming the audience, so it's okay.
Horizontal line. Will there be more than 2 groups?
No, I'm telling you there's only 2 groups.
Oh.
Yeah, so it's very clear that it should be here. Whereas, again, the purely supervised solution would do something like this. And the purely supervised would just look at these 2, and it would split them like that. And the semi-supervised, it says, no, I would much rather split them like this. It's a different from the supervised one. When we do Nystrom, again, we subsample the data, and we don't get the right answer. And it makes sense if you look at the subsample data, actually, because this gap here was small, when you subsample the data, you don't see this natural clustering anymore. So it finds a different clustering, which is not the right one.
How did your subsample get so badly distributed?
No, actually, it's there was no. It was the first random choice that we did. The point where we made this gap small so that a random subsampling would look bad. You're right, and there's a lot of papers on this, that if the eigengap is big, if there's a very clear clustering that's much better than everything else, then any subsampling of it will also look good. It's where subsampling really hurts you is when the original problem, the answer was not totally obvious. And so that's what we did here. But given that you have such a small gap, almost any random sample that you use will look bad. Because this gap is very small relative to the distance between points that you get from the samples. In contrast, we use all the data points, and the data, this particular distribution is separable, so we get the right answer. In contrast, here's data that's not separable. So So first, again, I'll ask you, what do you think is the right classification? Yes, the inner circle should be red, the outer circle should be green. Nystrom gets it correct, is because here, as again in response to Scott's question, even after we subsample the data, it's still pretty obvious what the right clustering is. Whereas we make a separable assumption that it is not separable, at least not in Cartesian coordinates. It is separable in polar coordinates.
So what's your complexity? What's the overall complexity of this operation that you have?
It's linear in the number of points. That's the important. It's cubic in the dimension.
If you were to start with your example and just do a random walk, which you would you would also get this kind of separation. Would be
Depends on your parameters.
What do you mean by random walk?
Or even if you were to do mean shift on this thing, you would also get.
Mean shift is actually very expensive. Every iteration of mean shift is. But yeah. But to do a random walk is very similar to the eigenvectors of Laplacian, right? I mean, those things are intimately related. But to calculate the random walk, at least in a naive way, you take something and you multiply and you multiply and you multiply.
Yeah, let me just elaborate a little bit on this because it's another way of thinking about all these Laplacian techniques. Some other people call it diffusion maps, which is essentially the same thing, which really build on this intuition that diffusion, again, those who ever saw the diffusion equation know that it's exactly the same thing. I mean, so random walks in space are the solutions of the Laplacian of some function equals the first derivative in times this Laplacian, and if you're looking for stationary solutions, you have precisely this type of eigenvalues. And now when you move to graphs or to non-uniform space, you get exactly the same story. And so mathematicians will talk about Brownian motion or diffusions on graphs, and we'll have exactly the same formalism. Very nicely integrated.
This semi-supervised solution, defined using eigenvectors of Laplacian, can also be formulated in the following random walk sense. If you say, if I start a random walk from each point, will I reach a red point before a green point? All the ones where I will reach red first, I'll color red. All the ones where I'll reach green first, I'll color green. And you can show mathematically that's exactly the same as the semi-supervised solution.
Yeah, but no, I'm not talking about just starting random. But if you were to start from the red and green and just start walking from there randomly, wouldn't you be coloring all the red ones and coloring all the green ones?
Yeah, this is
Same thing.
random walk.
No, but it's
If
not.
the gap is high enough, imagine that this is the beginning of a
You get
fire.
every point, you get 80 million points, you're starting that thing, you're going to get there in a short time.
Let's start with a random point, and you have to eventually. Oh, okay.
It could take you a lot, and you don't necessarily want to take the first one because it could be just by chance. You want to wait a bit. But yeah, these are it's still expensive.
This is a much faster way of doing the random walk.
Yeah, that's what I think of it.
You get to steady
Random walk is
state.
very slowly going to diffuse to the net. Just find the solution below.
But I just want to again emphasize that if the data is not separable, our technique doesn't work. There's no magic here. It uses a strong assumption of separability. And Nystrom, in that sense, Nystrom is a better algorithm because it makes no assumption on the data. It's more robust to this particular assumption. Okay, so I want to finish so we can move on. Experiments. So now we go back to images. And these are a subset of the tiny images was actually hand labeled by Canadian students, where the students were paid in order to look at these images. Like a dump truck is a Google query. They looked at all the images that Google returned for dump truck and labeled for everyone, is it really a dump truck, yes or no?
And there are 36 kinds of snow.
Because they're Canadian. Hockey. They have 36 words for hockey. It's amazing how fast these numbers grow. Even though the students were paid very little. Danielle is here in the audience, who was one of the labelers, but you were not paid.
No, I was in the pilot.
Yes.
The pilot still
He was still in the pilot. But once they started paying, actually it becomes, they managed to do something like 63,000 images.
It goes really fast. Signing you, so you just click.
But even these 63,000 images cost a fair amount of money, on the order of tens of thousands of dollars to label. and they made the calculation that to label the whole data set would be as expensive as a F-35 fighter jet or something. They decided not to spend that money. So it's interesting, really, how even if you pay people a very small amount of money to do it, these things grow. The price grows. So, but we do have a fraction that is calculating the price of the F-35. Maybe it's before taxes or after taxes. So anyway, but we're going to be using this for testing. At least we have a small subset of this images that are used for testing. Okay, the most important thing I neglected to mention is what is X? How do we represent the images of X coming from space? This was the question that Danielle also asked Michal. The simplest thing you can do is you can do a sum of square distances between the pixel values. We all know that's not a good visual metric. It's much better to somehow look at things that look at orientations of histograms. This was also mentioned in the talk when we were talking about the law of trigs and so forth. The standard way of representing similarity between images is you somehow, and this is one manifestation that is called GIST, and GIST works in the following way. You take your image, you divide into spatial bins, in this case 16. In every spatial bin, you have orientations. You apply Gabor filters at different scales and orientations. You sum the total energy, the squared activation of these filters. So that would give you one number for every spatial location and every orientation and every spatial frequency. So in this case, there are 16 spatial bins, 4 orientations, 3 scales. So that's 12 times 16, 100 and something, 184, I think, yes. 184 numbers, and that's our vector that corresponds to that particular image.
That's just a sketch, no color?
No color. I think they have reasons. Color actually can often be very misleading. It tends to overwhelm. Actually, if you look at Google similar images today, that's very predominantly based on color. And so if you have a picture of a sunset, anyway, the other things that get returned are predominantly things that just have the same color but have very different spatial arrangements. And you'll see actually, color histograms were used, it's amazing, embarrassingly a long time ago. But they have some advantages, but they can be easy to fool in these large data sets. So this does not use color.
Color histogram is a very special case of the bag of word model, essentially. Bag of features.
Yes.
Only color, because now we do much better special.
So, and you can think of these oriented things as also a dictionary, but the bag is not global. It's you only sum it over a spatial location. Okay, so the key question is, are these dimensions independent? Oh, 384, so that was, my numbers were off. And the answer is, if you look at the original pairs of features, they're not, and it makes a lot of sense if you know anything about vision, and go back to this descriptor. One number here is this orientation in this location, and the other number is this orientation in the same location, and those will be negatively correlated, typical, or anyway, they'll certainly not be independent. The same orientation at different scales will be very highly correlated. If the Gabor filter in this orientation at a fine scale fires, chances are the same is true at the coarser scales. So it makes a lot of sense that these would not be independent. And you can do this by measuring mutual information, Talib's favorite measure. And indeed you get mutual informations that are very high between different GIST descriptors. But if you do PCA on the GIST descriptors and just make them uncorrelated, then you get things that are not totally independent because there are still higher order dependencies, but the mutual information is very small. So after we reduce the dimensions, the separability, after we do the PCA, the separability assumption is very close to holding. Okay, so here's the experiment, just the protocol, the way it works. The task is not so much a classification task, say whether or not this is so the first class here is Airbus. Really what people care about so much is not, is this an Airbus, yes or no? It's not the binary classification, but you want to rank the images in some way. So you type Airbus into Google, it returns 1,000 images. Google really wants the one on the first page to be, with a very high probability, being truly Airbuses. So what we're measuring is our precision recall curves. That is, given that you're allowed to return, say, so 15% recall corresponds to about 25 images. So you take all the images returned by the search engine, you rank them according to your criterion, and you measure in the first 25 how many were really Airbuses. That's the task. Okay, so this is the first, on the x-axis is the log number of training examples. For some reason this is only on the positive training examples, and you have to remember that every positive training example for one class acts as a negative training example for the other classes, and the number of, but anyways, you need to multiply this by, I think, some number 16 or so. How many classes do you have? We don't even say it here. So the number, on the x-axis you have the number of training examples in the log space. So here you have 4 training examples per class, so multiplied by 16, I think, for the number of classes. 16. Okay. So 4 times 16, so there's actually 64 training examples here, and so on and so forth. And what this compares is the fully supervised algorithm, support vector machine, here, and it does very poorly, obviously, when there is only 1 training example or 2 training examples per class. It does actually worse than chance. But as things as you increase the number of training examples, it does very well, which is not surprising because it's supervised technique. And in the dark light blue, we see the semi-supervised technique, which just inverts this n by n matrix. Here n was not 80 million, but it was only tens of thousands. So we could invert it, and it does much better than the SVM for a small number of examples. And it actually blows up numerically when the number of examples increases. And then this is the Nystrom method, where you subsample. And again, it all depends on how hard you subsample. Typically, Nystrom works well when you subsample about 50% of the data. If you have 80 million images, you go down to 40 million. Nystrom works very well, but that doesn't really solve you any complexity issues. When you sample much more than that, the performance is bad. And in our technique, this Eigen function technique, it basically follows the least squares solution, but gets you there much faster, and also has a little bit less of overfitting. You can see, I don't know how significant that is, but the separability assumption somehow helps regularize the solution a little bit. And these are some other methods, like nearest neighbor, and so on. So on these 63,000 images, we do very well, as good as the high complexity semi-supervised technique, but with a much lower cost. On the 80 million images, we just can't do the light blue curve. We can't really invert this 80 million by 80 million matrix, but we can do our techniques. So we have 32 dimensions, use k equals to 48 eigenfunctions, and we pre-compute these eigenvectors and just store them in memory. So we do this thing that I mentioned earlier, where we do the histograms, do things along every dimension. And after we've done that, now we can do label propagation. Just solve this 48 by 48 matrix in real time. Whenever someone labels a new point, we can re-propagate everything, and it's very, very quick. In fact, Rob Fergus used to have a demo on his iPhone of basically propagating labels through this 80 million by 80 million graph in very 0.1 seconds per keyword. It's very, very fast algorithm. Again, because the number 80 million doesn't really enter into the algorithm anymore, because we've taken the limit. Okay, so here's Japanese Spaniel. And this is the original ranking from the search engine. So some of these are indeed dogs. I think some of these I have no idea what a Japanese Spaniel really is. It's probably a dog. But some of these were labeled as correct by the human and some were not. So we give it 3 positive and 3 negative examples from what humans labeled as actually being Japanese Spaniels. And then one simple thing we can do is this nearest neighbor re-ranking. We can re-rank all the images based on how close they are to a positive example or to a negative example. And for some reason, this brings up some weird things that don't look like. I don't know what the Japanese spaniel is, but I'm sure it's not that. And then our eigenfunction re-ranking, because it's basically using the unlabeled data as well, and it propagates for the unlabeled points, it does much better. Here are three more classes. Again, the top is the original re-ranking. The left is the original re-ranking. The middle is nearest neighbor re-ranking, and the right is our method. And I think the main point is really that it finds things that are. It could be that these were also Airbuses. I don't know, but it finds things that are more similar to what the human labelers labeled as Airbuses or ostriches or autos. Let me just conclude.
These are all global similarities, right?
Yes, yes. This is just, you take the entire image. And these images, I should have said, are actually stored in memory as 32 by 32 thumbnails. So it's hard to do too much with part-based methods because you don't have a lot of pixels there. Let me just summarize. I think there's a summary of this talk and there's the broader take-home message. For me, the broader take-home message is this is a really exciting time to be doing computer vision. We have billions and billions of images out there. That's got to be useful for something, and we can use it. We may be able to use this to really leverage these gigantic data sets to really make breakthroughs in classical computer vision tasks. I've talked about a very specific instantiation of this idea, which is how to do semi-supervised learning, and it's a scheme that can scale to really large problems because it's linear in a number of points. The basic idea is instead of subsampling the data, take the limit of infinite data. In order to do this, we need to make a strong assumption that the input data distribution is separable. But when this assumption holds, we can propagate labels in a graph with 80 million nodes in a fraction of a second. Thank you very much.
Thank you very much, Yair. Any further comments, questions? I think I'm going to open the air conditioning again.
Yes,
The robustness to listen the fitting of the CDS, how robust is it to outliers and adapters to skews and stuff like that?
Yeah, that's a good question. We actually, the code we put on the web discards it only takes the 5th to 95th percentiles and does everything else out. So that gives us, the only robustness we have to outliers is that very simple trick.
Set of predefined family of distribution that you work with?
No.
No.
It's non-parametric. It only assumes the separability assumption, but along every dimension, we just build a histogram, so it's completely non-parametric. But it's true that if we have a large number of outliers, I mean, the only thing we have to keep us, to save us from outliers, the only thing that helps us is this 5 to 95 percentile. You could do something much smarter. It's a good idea. So somehow take the outliers, given the distribution you already learned, try to estimate what the outliers are, but we didn't do anything like that.
In this kind of method, all you know is that the easy examples you find. Right? That's what the NES said. You can find the easy example. Anything that's a little complicated, you have no idea, so it should be down on the list somewhere.
I don't know. So things
That's what you're measuring. You're measuring that you can find the easiest 25 things in the class. Many pictures or something like that.
Oh, you mean
millions of hard examples, you have no idea if you do well or not.
in the measures, nothing with the technique, in measuring that area of the precision recall. Yes. I think you could always...
Google gets by with that, but the question is that's a good answer for everything.
Yeah, you could certainly do the whole thing and do the full precision recall curve. But it turns out, I think for most applications with very large data sets, assumption is there will be some easy cases in there anyway. So
that's all you get.
So I think it may be, and you don't want a person to go through. I mean, I think that's people just don't click on the second page. I think there's some statistic about this that 99% of people don't go to the second page. So you really want to focus your attention on the low recall rate. But yeah. But it could be that we actually are doing worse, much worse than the others in other cases. Yeah, we did try that.
So I'm troubled by the fact that eventually not only that you move to the continuum, that you move to Gaussian. You depend only on second order statistics.
No, that's not true. This is maybe also what Yair was saying. We second order statistics, we use that to find the best rotation.
Yes.
That's the,
Right.
but per rotation we build a non-parametric estimate. So we don't assume any parametric forms. It could be complicated, could have multiple
Eventually
clusters.
you control only the second moment. I correctly understood.
No, it's the only thing, the second moments only control the rotation.
Yes.
But if you look at
Go back to the algorithm?
the basic example we always have, the toy example. So,
It's Gaussian after this tree, the Laplacian tree.
oh, you're saying in its high dimension.
In high dimension, it's essentially a quadratic.
Yes, this is true. In high dimension.
So really what takes care of the nonlinearities is really the eigenvalues of this.
Yes, but those are very nonlinear, as you know, very nonlinear
Right,
functions over there.
This is the trick. It's again, it's actually related to my talk and to your talk before. I mean, covariance. Why covariance is good? I think it boils down to one good method that we have in machine learning, which is
PCA.
it's actually the kernel trick. I think it's a different type of kernel. All right. So
does Google today use anything other than labels when it does image search?
Yes. I don't know exactly what they do, but I can tell you what Microsoft thinks they do.
Okay.
Which is, they use classifiers, at least for the popular queries. They actually have trained classifiers to do this re-ranking. Again, this is all second-hand information, but certainly if you look at the number of computer vision people they've hired in those 3 years, and the number of people who work on image search who know how to do object detection, and so they have a lot of computer vision now in the image search.
I think the connection to security is quite obvious,
Okay.
but also should see. Anyway, thank you again, and we move to the next topic. So we had to have some representative of Tel Aviv University. I'm sorry, do you know?
No, thank you.
No, but remove everything.
You know what it is.
Sorry, I posted to state on how it goes. So you had Bengal with his student, a big group. You tell us about using target-based Bayesian nets for suspect monitoring. This is actually directly related to security. That's a so, and that's what we
would like to say that I'm grateful for the organizers